So, what was my d tau? It was like r squared dr sine theta d theta. There it is, down the bottom. Oh, okay, so let's write all this whole thing out. And r goes from 0 to infinity. R squared dr, so let's put all the r squared stuff together first. I'm going to have an, oh, we better, I don't want to screw up, right? Let's put it all together. Hey, are there any i's?
No.
No, so I'll just be writing the same thing, what? Twice.
Yeah.
So let's do that. This will be squared, and this will be e to the negative, what?
2r.
Yeah, negative 2r over 2a naught, but those 2's are going to cancel on you.
Would it be 4a stuff, or just
Take e to the negative r over 2a naught times e to the negative r over 2a naught. You get e to the negative 2r over 2a naught, which is e to the negative r over.
No, you're just adding the fraction.
Add exponents.
The thing
Oh,
on the
that's
fraction
true.
you're adding them.
Okay.
Yeah, it's in the denominator.
Okay. Add exponents.
Oh, Dr. Smith, I was gonna say, what is that? Like, what do you mean if you? How would you know if you have an eye? Would you actually have like an eye?
Yeah, you gotta physically see an I in there.
Oh, okay.
I wish there was. Then it would go away, right? Okay. And then it's, we can do our, it doesn't matter to the order of this stuff. I'm just following the order of my d tau that's on my cheat sheet here. So there's, I have no thetas, but theta goes from 0 to pi. None of this I'm memorizing, right? Realize that. I'm not memorizing any of it. I've been doing this for years, and I'm still looking at this. Because why memorize it? Sine theta, d theta. Phi goes from 0 to 2 pi. D phi. Let's change colors here. Okay, so 1 n squared. Integral 0 to infinity. Okay, do that stupid FOIL thing, right? Ah, so I'm going to have, I don't do FOIL. First I'd multiply through by 2, then there's got to be a cook. What is this? Just read it out to me.
Yeah.
4r over a naught plus
R squared over it. All right, everybody agree to that with that? That'll save us some time. Okay.
Just agree.
Oh, I forgot about my R squared. God, I'm going to write all this again. Well, I can finish this part though.
Yeah,
What's all of this equal?
4
From a
pi.
concept preview. It was 4 pi?
Yeah.
All right, so we're done with that. All right, that's the concept preview. Everybody agrees? Because I could screw up here. I don't have it memorized. Okay, and then what you guys do? Let's multiply through by that. See what the game plan? The game plan is to multiply through by that r squared, e to the negative 2r over a naught, and make it 3 integrals. Then I'm going to have to use that special little, on the cheat sheet, that exponential integral, do it 3 times. I can take that 4 pi all the way out. So I'm going to make 3 integrals here. So I'll have 4. Oh, I can take that 4 out of move it out the front. 4 r squared e to the negative 2r over a naught dr. There's the first one. Right? And I pulled that 4 out, so it'll be a lot, I don't know, so my brain can see how to do the integral easier. Make sense, Ashley?
I don't understand like the 4 minus the 4r.
This part that,
Yeah.
okay, so what I don't, see, Ricky's got the FOIL thing memorized. Me, I'm going to multiply since I've never memorized FOIL, first I multiply through by the 2. Multiply through by the 2. So I'll have a 4 minus 2r over a naught. All right? Then I multiply through by the negative r over a naught. Negative 2r over a naught plus r squared over a naught squared. See, when you multiply through by that one. So then you get all this stuff. You combine it, get that. But he was right. Man, how could we doubt him? Crazy.
Oh, Dr. Smith.
Okay.
I thought you said the 2 cancels from e to negative 2r, because the original.
Oh, did I write the 2 in there again?
Yeah.
Yeah, we didn't. We should have canceled it out right away. I was trying to show all my work. I shouldn't have done that. Thank you very much. So let's keep canceling that. All right, now let's do the other integral. Now it's going to be a minus. Pull out all your constants. That looks like a 4 over a naught that I'll be pulling out. All right, and it's a negative 4 over a naught. Now I have an r times it. That'll be an r cubed. Right? E to the negative r over a naught. One more term. The constant will be a 1 over a naught squared. All right? So now I'm pulling out this term. I have an r squared times an r squared. That'll be r to the 4th. And I'm consciously trying to get things in the format as I'm writing this, because I know what's headed up. I'm trying to get it in the format of what's on this cheat sheet, where it says the integral of x to the n times e to the minus ax. That's why I'm always putting the r in front of this and getting all those constants out of there so it won't confuse me when I'm doing this. So Brad, you see the game plan? Okay, so be careful with your notation. Then things are much, much smoother.
Yeah.
They really are. E to the negative r over a naught dr. Okay, now we just have to do it 4 times. Okay, look at the integral. My little n is going to be 2 over over.
Pull all that stuff out like that.
There's no other way. I know.
Exactly.
That makes sense. Because you want to set it up like the e thing.
Oh, I guess you could integrate by parts or whatever. You guys like doing that? Oh, I hate that.
No, we didn't do that. Like we thought that like you could take that e to the negative 2r over a naught r squared, and we did our formula with that. And then we tried to integrate 4 minus 4r over a naught plus r squared.
Oh, no, always break up integrals.
And it came out to infinity, and we're just like,
Yeah. Always break up integrals. It's so much easier. Okay, now my a is it's e to the negative ax.
So it's 1 over a naught.
So it's 1 over a naught. Perfect. Excellent. Minus 4 over a naught. Now I have a 3 factorial. And my a is the same thing, right? 1 over a naught to the 4th. One more term, plus 1 over a naught squared. Now I've got a 4, so that's be 4 factorial. All over 1 over a naught. Everybody to the 5th. Well, Bob will see it. Might as well just finish this silly thing, right? Okay. So I don't want to screw up, so I'm going to write 4 times 2 times What can I do with that 1 over a naught cubed? Where does it go? Flips to the top. Three times 2 is 6. A naught to the 4th. Okay, now one thing that I really like to see, I can group terms. Looks like a naught is to the 3rd power. This is looking promising. If they wrote the question, they were planning all this, I guess. They may not have. Okay. 4 times 3 is 12, times 2 is 24. Oh, the last two cancel out on you, don't they? It's really nice. So my n is going to be what? It'll be 32 pi a naught to the 3rd. Because 8 times 4 is 32. Pi a naught to the 3rd. Yes.
Yeah, for some reason I wanted to do that too. Make 8 times 4, 24.
No, I actually wrote a 6. I don't know why I was
Oh, really?
Yeah.
And that's what I'm pretty sure that sounds right. It was pretty smooth. Oh, but you're not done because they want you to write the normalized wave function. So often I end up taking off points because people don't finish their answer. Write the normalized wave function. So what is it? You have to write it. Psi equals the square root of 1 over 32 pi a naught to the 3rd. 1 over all that. And times my wave function, which was 2 minus r over a naught. Oh, man.
Plug your n back into your wave function.
Times 2 minus r over a naught e to the negative r over 2. So that's your final answer. All right. So just put your n back in. Pretty much just multiply your n by this thing. You're following this.
Okay.
So if you can do this one, man, what's on that handout is going to be patty cake.
Okay, so you took whatever you got for n and you put it where?
Remember, follow these two. These are your two starting points.
Okay. You put it back.
This is how you write your normalized wave function. N times your trial wave function, whatever they want to call it, right? So we know that our trial wave function was what we started with. Let's multiply this by n. It'll be normalized.
Just multiply that times n?
That's what this says.
Okay, we don't have this. Where? Okay.
So then you can just write it all through again times the rest.
Take n times that, and that's your answer. That's your normalized wave function. So then if you do this, you are definitely going to get 1. if you use your normalized wave function. I mean, that in itself could be an exam.
Yeah.
You normalize a wave function, and then you prove that it's normalized, right? This would be a good one, right? You just found the normalization constant. Now you got to prove that it's normalized. Pretty much you just do it all again. You're going to do the exact same thing again, but you're going to end up with things are going to cancel out. You're going to get 1 equals 1.
And square one would be pulled out.
Let's make it Facebook official.
Yeah, it's going to. You're going to take n squared. The square root disappears.
Okay. Wow.
It'd be really redundant, though. Okay. So here's some easier ones.
Yeah.
So realize, not only do I want you to normalize it, I want you to write the normalized wave function when you're done. Right? So just like we did.
Okay.
So find n, but then go back and write your normalized wave function. So you're going to have, your function is going to be something times 6. It's going to be your final answer. So try these. You're in a box of length L. So x can only go between 0 and L. So in your starting point, in every single one of these questions, what will d tau be?
X.
What? dx. Exactly. If you can see that, you're on track to do this. If you can see that d tau is going to be dx in every single one of these, you're done. You got it. You have a good start.
And you do that just because the only variable you represent is your
Well,
Because you're weighing-
well, no, not really, because look at over here. There's no theta or phi in here, but we had to use it because we're integrating over all space. They didn't give us any limits, right? They just said normalize it here, so you have to assume all space. Here, you don't assume all space. You just assume x can be between 0 and L. So now all of a sudden, now they've narrowed it down not only to one dimension, just dx, but they've narrowed it down that x can only be between 0 and L. So in every single one of your limits here, what will be your integration limits?
0 to L.
0 to L. And this is just going to be dx. And that's from the problem itself.
Scroll back up. First one, yeah, like 6L problem, I think.
Is that how we're writing?
So when you're saying when it gives you the multiple ranges?
What are you talking about right here?
Yes.
Yeah, did they say in the question that R can only be between 2 and 3? No, or nothing like that. So they didn't. They just said normalize this. So you have to, it has to be over all space, all 3 dimensions.
di equals dx dy.
dz, or d tau is r squared dr sine theta d theta d phi, which is what it is for this one because you're in spherical polar coordinates.
Okay, because it's an r.
Yeah.
Okay, since the other one tells you just that one range.
Yeah, it has to be one dimension, and your x is really confined, only between 0 and L. So try these.
Try it.
Yeah, that's what I was.
Mhm.
I have a question. So what would be
The side. Or the.
Is it the wave of a function?
So we're going to do A. Where's your other starting point that I really want you to write?
N. Oh.
What I want you to write.
Psi
How do you write this?
and
Oh.
Big psi equals what?
and V.
And phi. Make this a habit.
But
And now, no, just wait. Now keep going. How do you write your psi now? How would you write it for this part A?
Is that the 6?
so the N is
L.
N times what's your trial wave function? What's the function I want you to normalize? 6. So that's what notation does for you. It takes all questions out. There's nothing to question. You have to put in only what they want you to put in, nothing extra. They want you to test 6. Doesn't sound like much of a function to me, but that's what they want you to test. So fine, you put it in.
So then f of x could also mean that, what's the sign symbol? The one that looks like the star and the...
This?
Psi. Trident.
They call psi, and they call this one phi.
Psi?
So psi, but it really doesn't matter what it is. It's also right here. This is your other starting point. This is what you have to put into this normalization. Well, what is that? It's this. So don't worry about what it exactly looks like. It just has to be the exact same thing. We could call it z, or not, z's a bad one. Call it q. Q star q, where q is this times this. It doesn't matter what variable you give it.
Right.
It's just this is their tradition. So
Then f of x is considered psi then?
f of x,
Would be considered psi, or
you know,
just a function?
this is psi, this is phi. How you write phi? Oh yeah, that's right, phi. Right? That's phi. So which one is f of x? Has to be phi. Yep.
Looks so much like a 4. I always have to tell myself that it's not. It's a 4.
The size?
Yes.
Not a 4. What's a 4?
What do you think?
You mean triangles.
I didn't even precise it.
Aha! You did it. You didn't finish the question.
Oh, damn
You swore on. So Pablo got for n 1 over the square root of 1 over 36L for n for A, for part A. See if you get
Is that before or after you
n is the
simplify
square root of 1 over 36L.
it?
Right? That's what you got? This is what he got for his n. See if you can get that. I don't know if that's right or not. Just that's what you got.
That's what I got too.
Oh, did you? All right.
I just simplified it a bit more.
Oh, yeah, you could say 1 over 6
Yeah,
times the
it's
square root of 1 over L.
6 third L.
That sounds better, doesn't it? I didn't even realize that. All right.
You know, just do it. I mean, you have to do it. The integral. Yeah, remember when you have a constant, when you get the integral, you just put x on it.
So it's
When you, yeah, it'd be 36.
Oh, then times 6,
No,
you just end up with 1 over the square root of L.
No.
Interesting.
Right. Psi is just 6, right?
Yeah. So your 6 is going to cancel. You just end up with the square root of 1 over L for a final answer for a normalized wave function.
Yeah, there you go. 36x.
36x.
Yeah, then you got
Interesting.
Yeah, you
So that's part A.
Oh, so psi is going to equal 1 over square root of L?
Remember what psi is? You have to take what times what?
And
N times phi.
So phi is 6?
Ask Ashley.
Ashley, what's
Okay, let's work that one out then.
1/36, like that. That's where I get confused. Because I think that it just stays as 36.
Did you get this answer? Well, let's work it out.
No, like right now I'm on n, like I'm on n squared 36 L, right? But why is it always like 1/n?
Because you have to solve for n. Aren't you solving for n? That's the whole purpose. So it's always going to be 1 over something,
Okay. Yeah.
right?
Sorry. Okay. Yeah, I get it.
So once you get a normalized wave function for A, B, C, and D, you do part 2.
Okay, I got it.
Okay. So I want to make sure we set up a part 2 before you leave, but let's see how far you can get.
Part two would be.
Number 2 there.
Oh, because I know it says.
Question number 2.
Okay, well, it's just to copy everything on here too.
Oh, sorry, not that far. I'm just talking about. Oh, sorry. Why is mine different than yours?
And then it's got this for each normalized wave.
Yeah, I want you to do right.
Okay,
Do
so
that.
after we do it, then we gotta copy.
So I gotta write that. Reach normalized. Why isn't that on here?
Yeah, so you gotta put 0 on the bottom and L on top. So we'll put.
Yeah, we have to add that on there. Why yours has it? Still playing catch up. Yeah.
You did integrate it before you put it in brackets. Before it was 36. You got it?
I did it wrong.
You get them all?
Sorry, I forgot about those little ones. Okay. Oh, it's back here.
So I'll be the fellow that's right.
Yeah, but the 6's cancel.
Okay.
All right, so you just get 1 over the square root of L.
So it'd be,
Mm-hmm. Perfect. Yes. What equals psi? That'll be easy. Yes, because that'll make it easier to do part 3.
So n equals 1/36 L squared. The square root of 36.
Yeah, square root of 1 over 36 L. Yeah, you can just make the top a 1 since the square root of 1 equals 1.
We just simplify that down there.
Get to 1.
It's 1 over 6.
Yeah, you should say this is 1 over 6 times the square root of 1 over L.
Times the square root of 1 over L.
Yeah, times square root of 1 over L. That's your n. And then you got to put that into your, to write your normalized wave function, has to be n, which is this.
Mm-hmm.
I wouldn't do an x because that's going to look like an x, right? And then yeah, a dot, right? Take this times this, and then you have your psi, your normalized wave function.
Okay.
So the 6's end up canceling.
Right.
Psi ends up just being that.
Okay.
Say 1 plus 6 times 1 over 6. And yeah, and then you just have to 1 over square root of L. And whatever you get is going to be this. It's the side of everything.
Yeah.
And it's going to equal n times n is what you got. And times 6, so it's just going to equal square root of L. And it's going to be backwards.
See? Dude, have this out. Have this out. It's going to help you.
Yeah. That's what's gonna do.
Have this out in front of you. Tear that out and...
I'm afraid I'm gonna lose it if I tear it out from my book.
Yeah, well, if you tear it out, then you're always going to be using it.
Oh no, I do use it. I'm just afraid I'm gonna lose it.
No. Take a picture of it with your phone. Then you can always print it out again.
A separate one, like a torn out one, that way I can make copies.
Just take a picture with your phone. And then you can print out as many as you want.
I'll go upstairs and scan it.
This one.
I'll get it from your other class.
Okay, a few more minutes, then we're going to jump to do a number 3.
Did you get an answer for the second one?
3 over L to the third square root.
You got this for n. You got this.
Yeah.
Okay.
That's a 3 and a 3 and a out, right?
Yeah, that's a square root of 3 over L to the 4th.
Yeah.
Yeah? Okay. What did you say, Ashley? Is that what you got?
Let me write down what you just said. For B, n is what?
Oh, okay.
And is this?
3 over L cubed square root times what? Oh, that's it?
No, either normal.
Yeah, so that's your n. 3 over L cubed square root. Okay, thanks.
Yeah. Yeah, square root of 3 over. Let's see what you get.
Okay, so I want to just have you pause for a sec, 'cause I want you to do at least one of the part 3s. It's not typed up here, but it says determine the probability that a particle is be between, oh, that's my 2.
Yeah.
The particles between x equals 3 and x equals 4 for box of length L equals 7. So what that is that's probability density. So what I do, my starting point is I do this. And this only works for normalized wave functions. Because that's why we normalize it. Because if the probability is 100%, it means something now. So all we're going to do is put in our limits, what they want, and put in our normalized wave function. And whatever we get, you get 0.25, that means 25%.
So we've all been working these under the assumption of a 1 or 100%.
No, now there is no assumption. You forced it to be 100%. If I do all space, for negative infinity to positive infinity, or 0 to L, 'cause that's the box, you're going to get 1 now, because you normalized it. Right? So now we don't want to go do the whole box, though. We want to go just between x equals 3 and x equals 4. So this is how I start. So that probability, again, I'm substituting exactly into this thing. Verbatim, the integral, psi star psi. So I'm doing part A here. So what's my psi? This is it. Are there any i's?
No.
No, so it's the same thing twice, but let's not confuse you. Let's just write it twice. The square root of 1 over L times the square root of 1 over L d tau. So just write
R squared is same as
what now our x disappeared in our function, but you know what the original trial function was. Are they in spherical polar coordinates? No. It's just what then? D x. There is no y or z, right? And there's another hint. Remember, x equals 3 to 4.
Yeah, they don't give you intervals. For
There's nothing else. If they did, then I would definitely be doing the dy dz. So where do I put these limits, 3 to 4? Put them on the integral. So that's the integral that you solve. So I don't have any x's here, so it's safe to pull this out. And that's just going to be 1 over L. And they said that L was 7. So you can substitute that in now or substitute it in later. It's up to you. I kind of save it for the end, but it really doesn't matter. Probability equals 1 over L. Well, we'll go inside the antiderivative. X. All right. So I'll have L is 7, 1 over 7, times 4 minus 3, which is 1. So I'll have 1/7. That's my answer. So you can write it in decimal format or just leave it as 1/7. 1/7 sounds like a good, you get an idea. What's the probability? Oh, it's 1/7. Kind of makes more sense than putting it in decimal format. Okay, so that's what you do for part 3. You take each of your normalized wave functions and substitute them into the probability density expression. Do you see any x's here? So what do you do with it? Just pull it straight out. And I'm just getting lazy now because I'm hoping that I want you to make these jumps instead of writing all these little steps. But if it helps you, write it, right? So you'd have 1 over L times integral from 3 to 4 dx, right? Just go ahead and write it then.
I've gotten 1 over L for a final answer.
Yeah, 1 over L. But what's L?
tells you L is 7 equals 7.
L squared? Oh, okay, okay. Good.
That's why I said you could plug it in from the
I was like,
beginning.
I didn't know where that came into play.
You could plug it in at the very beginning.
Okay. Well,
But it's kind of nice to wait to the end because you get fractions very often as an answer.
okay. I don't know what's going on in here, but that's just so funny.
Yeah, it is.
Okay, so we don't care, or what do you call it? Does the integral cover the width and the height of the box and the length?
Wait. You're using a lot of terms here. Width, height. How many dimensions are you talking about?
1.
You're talking about 3. When you start talking about width and height.
This
No.
one's 1. Right?
What did we say at the very beginning? What is dx for every single one of these? Or sorry, what is d tau for every single one of these?
Just
D tau is just dx. So you can't use the words width and height.
yeah, it's just a point on a line.
Yeah.
Yeah.
For these problems. So it's not confusing if you
Yeah, now it's
trust what I'm saying is it's not confusing in this perspective. The math isn't confusing because it's very detailed. It tells you exactly what you got to do. And you do nothing less and nothing more. You do exactly what it says. And no more.
So the probability equals 1/7.
The probability is going to be 1/7. Yeah. 1 out of 7.
You said you can either put it in fraction or in decimal.
That doesn't matter. I like 1 out of 7. It makes more sense in my brain.
I'm sorry, just for clarification's sake. So everything that we've done up into part 3, we were saying probability was 100%, correct? That's why we have a 1.
Well, hey, I think you're missing the point. The whole point of normalization is so that you and I can talk about probability. Because you want to normalize it. In other words, you write this weird, funky equation, and you want to talk about the probability of this particle doing this, or the probability of it being here or there. You want to talk about probability. Well, to you and me, probability only makes sense if you know what's going to happen. If you know what's going to happen, the probability is what? What number? 100%. And that's just our tradition. So we normalize to 100%. If you and I would have lived our whole lives and said, no, 200% is when things really happen. Just pretend. It's just a magic number, 200. Instead of 100, why? It's just a magic number. 200. 212.6. 212.6 is when something happens. You'd have to normalize to 212.6. So then in this expression right here would have to be 0.2126 if that was our convention of talking about percents. But it isn't. It's 100%. So, and they don't even want to use the percent symbol. 1 is just easier because everyone knows 0.9 is 90%. So that's what they do. So you can't talk about percents and probabilities until you normalize. After you normalize, then you can talk about probability. Because look at this. Here, again, the notation tells you these are psi's. These are normalized wave functions, right? These are normalized wave functions. Well, you got to get it normalized first. So here's your trial wave function. Whenever you want to normalize anything, that's what the equation is calling a phi. Whatever you want to normalize, they're calling it a phi. When you finally go through all the work of getting it normalized, multiply your phi by your n, now you call it psi. And then you have 2 equations that you can use. You can use this one, which won't give you anything new, because it's just 1 equals 1. But this one makes sense. Put in limits. This equation is really the same as this one. It is, because here you're just not integrating over all space. They're just changing the limits. Here they're integrating over all space. So if you want, you could add some stuff to this. You could say negative infinity to positive infinity, and here write a to b to show that they're different. Okay. So we're about out of time, but come by, try these out and come by.
And so we're going to have to do handout day 3 when we come in on Wednesday.
No, let's see. You're on day 3 right now, handout day 3.
Yes, but we'll
So,
turn that in.
yeah, you turn that in along with the homework and bold words for day 4.
Okay.
Yeah.
So we just turn in bold words today?
And the homework.
Yeah,
Well, I thought you, well, only if everyone's done with the homework. Otherwise, all right, well then, turn in the bold words and homework, then you have to worry about that. That'd be a good grade for you.
Then we do handout 3.
So the only thing due then next class period would be the handout 3 and bold words.
I'm sorry.
That'd be nice.
It would be terribly inconvenient to keep the homework, because I'd like to use it for this.
Then don't turn in the homework.